In this video, we're going to explore database join operations. Join operations are essential for combining data from multiple tables using relational algebra. This is a fundamental concept in database management, allowing us to create meaningful relationships between different sets of data. Let's delve into the inner join. An inner join returns only the matching rows from both tables, based on the specified join condition. Put simply, it only includes records that have matching values in both tables. To illustrate, imagine two tables, Table A and Table B. The inner join will return a new table containing only the rows where the key column in Table A matches the key column in Table B. Here's the SQL code for an inner join. Select asterisk from Table A inner join Table B on Table A.key equals Table B.key. This SQL statement will select all columns from both tables, but only for rows where the join condition is met. Next, let's discuss outer joins. Outer joins are used to return all records from one table, along with the matching records from another table. There are three types of outer joins: left outer join, right outer join, and full outer join. A left outer join returns all records from the left table and the matching records from the right table. If there is no match, null values are used for the right table's columns. The SQL code is: select asterisk from Table A left join Table B on Table A.key equals Table B.key. A right outer join returns all records from the right table and the matching records from the left table. If no match exists, null values are used for the left table columns. The SQL code is: select asterisk from Table A right join Table B on Table A.key equals Table B.key. A full outer join returns all records from both tables. If no match exists, null values are used for the columns from the table without a match. The SQL code is: select asterisk from Table A full join Table B on Table A.key equals Table B.key. Now let's examine the natural join. A natural join is a type of join that creates an implicit join, based on the same column names in the join tables. It automatically matches all columns with the same name, and duplicate columns appear only once in the result. No explicit join condition is needed. Here's the SQL syntax for a natural join. Select asterisk from Table A natural join Table B. For example, consider two tables, employees and departments, with a common column called department_ID. A natural join will automatically join these tables based on this common column. In the result, the department_ID column will appear only once. So if we have a table named employees with columns like EMP_ID, name, and department_ID, and a table named departments with columns like department_ID, department_name, and location, the natural join will combine these tables where the department_ID matches. Let's explore the theta join. A theta join is a join operation that uses any comparison operator in the join condition, not just equality. The comparison operator is represented by the theta symbol. This includes operators such as equal to, not equal to, less than, greater than, less than or equal to, and greater than or equal to. When theta is the equality operator, the theta join becomes an equijoin. The SQL syntax for a theta join is: select asterisk from Table A, Table B where Table A.column 1 theta Table B.column 2. For example, to find all employees whose salary is greater than the average salary of their department, use select E1.emp_ID, E1.name, E1.salary, E1.department_ID from employees E1, employees E2 where E1.department_ID equals department_ID and on salary greater than E2.salary. Another example is to match products with orders, where the quantity ordered is less than the product's stock level. The SQL code for that is: select P.product_ID, P.name, O.order_ID from products P, orders O where O quantity less than but stock_level. Let's compare equijoin and natural join. An equijoin is a type of theta join that uses only equality comparisons in the join condition. It explicitly specifies which columns to join on. The SQL code is: Select asterisk from employees Equijoin departments D on at department_ID equals .department_ID. A natural join, on the other hand, automatically joins tables based on columns with the same name. It doesn't require an explicit join condition and eliminates duplicate columns. The SQL code is select asterisk from employees natural join departments. Some key differences between them are: Equijoin requires an explicit join condition, while natural join is implicit. Equijoin can join on any columns, but natural join only on same-named columns. Equijoin keeps all columns, including duplicates, while natural join eliminates them. Also, Equijoin offers more control over which columns to join. Let's consider some performance aspects of joins. The order in which tables are joined can significantly impact performance. Join smaller tables first to reduce the intermediate result size. Consider table cardinality and selectivity of join conditions. Remember that most database optimizers reorder joins automatically. Indexing strategy is also very important. Create indexes on join columns for faster lookups. Foreign keys should be indexed in most cases. But be cautious, as too many indexes can slow down write operations. Different join types also have different impacts. Inner joins are typically faster than outer joins. Natural joins can be unpredictable if the schema changes. Complex theta joins may require full table scans. To optimize, select only the needed columns instead of using select asterisk. Use where clauses to filter data before joining. And consider denormalization for frequently joined tables. Now let's examine some common join implementation algorithms. The nested loop join algorithm works by, for each row in the outer table, scanning the entire inner table looking for matching rows. This is simple to implement, but inefficient for large tables. The time complexity is big O of n times m. The hash join algorithm builds a hash table on the smaller table, using the join columns as keys, then scans the larger table and probes the hash table for matches. The time complexity is big O of n plus m. The sort merge join algorithm sorts both tables on the join columns, then merges them in a single pass. This is efficient when the data is already sorted or when the result must be sorted. The time complexity is big O of n log n plus m log m. Lastly, the index nested loop join algorithm uses an index on the inner table to find matching rows. This is much faster than a regular nested loop join, when appropriate indexes exist. The time complexity is big O of n times log m. Let's consider some common pitfalls in using joins. One pitfall is the Cartesian product explosion. Missing join conditions can lead to Cartesian products, where every row from one table is joined with every row from another, causing exponential growth in result size. The solution is to always specify proper join conditions and verify result counts. Another pitfall is duplicate results. One-to-many relationships can cause duplicate rows in the result set, especially when joining multiple tables with such relationships. Use distinct or group by when appropriate, or restructure queries to solve this. Null value handling is also a common pitfall. Null values don't match anything in joins, including other nulls. This can lead to unexpected missing rows in inner joins. To handle this, use outer joins or coalesce/if null functions to handle null values. Lastly, column name ambiguity can also cause problems. When tables have columns with the same name, ambiguity can cause errors or incorrect results, if not properly qualified. To avoid this, always use table aliases to qualify column names in join conditions. Let's summarize what we've learned about join operations. Joins combine data from multiple tables based on related columns. Different join types serve different data retrieval needs. Join performance depends on algorithm selection and indexing. Proper join conditions prevent Cartesian products. And understanding null handling is crucial for correct results. There are some best practices to follow, like always specify explicit join conditions, use table aliases to avoid column ambiguity, Create indexes on frequently joined columns, select only needed columns, rather than using select asterisk and test queries with representative data volumes. In the future, explore advanced join techniques, such as self-joins and cross-joins. Also, explore subqueries and join alternatives, and query optimization strategies. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.